So when we read things from the literature and see what other researchers did, maybe they don't work in the same extreme environments that we do. The knowledge they gained is very important for us. We learn from it. We learn from others' mistakes. After we learn from others' mistakes, then we have to do our job to be sure that those parts will perform very well when they go to the application.
The challenge often is getting industry to change how they do things. There's a lot of innovation and technologies that come out of a university. These technologies can provide substantial or even incremental improvements on processes and performances. And so a large challenge that I find is convincing industry of the translation of academic research.
I'm Mostafa Yakout. I'm an assistant professor in the Department of Mechanical Engineering here at the University of Alberta. I'm also the director and founder of Alberta Next Generation Additive Manufacturing Laboratory, and I am the co-lead of materials and manufacturing team within the Center for Applied Research on Defense and Dual-Use Applications. And I am the Deputy Executive Director of the Alberta Advanced Manufacturing International Hub.
My name is Jamie Hogan. I'm a professor in mechanical engineering and the director of the Center for Defense and Dual-Use Technologies here at the University of Alberta. My lab researches material behaviors in extreme environments. So in hydrogen production, in reactors, there are extreme temperatures, extreme corrosion conditions, and then in addition to the hydrogen that exists in these reactors, and altogether these conditions create harsh environments for materials to survive. In addition to energy, I work on a lot of defense-related problems. So things that fly through space, or things that are underwater, or things that drive over land. In these defense scenarios, these materials and structures are subjected to high temperatures, things like blast and impact, and sometimes chemical environments. So there's a lot of relationships between the energy problems and the defense problems, in that materials are experiencing behavior under these more extreme conditions. Materials in advanced manufacturing intersects most of Canadians' lives, right? Whether it's health, whether it's energy, whether it's agriculture, whether it's mining, and then my focus area of defense.
Our focus is mainly in materials modification or materials development, particularly laser additive manufacturing solutions for next generation materials like high temperature materials, or materials that contain critical minerals, and materials that can work under extreme environments. We develop manufacturing solutions for processing those materials. Those materials are very hard to process in terms of manufacturing. So we identify manufacturing protocols to produce defect-free components that can be used in various applications, particularly in the energy sector, and that include nuclear and hydrogen energy applications.
Machine learning-based approaches are integral to what we do. They allow us to either exercise these models or solve these models or apply these models more rapidly for materials and structural design. The challenge, though, is getting enough data. So it would be very challenging to get enough data just by running experiments. These experiments take time, these experiments cost money, and so what we want to do is use experiments to validate multi-scale models, and then we want to exercise these multi-scale models to generate data that we can then use in machine learning-based design approaches. Microstructure-based design of material means the following. Within a material, it has different microstructural features. So it has grains or grain boundary features. Within these grains, there could be different element types. And what we want to do is understand the role of grain and grain boundaries and element types on mechanical performance or corrosion performance or overall behavior of these materials in these extreme environments. We want to develop physically informed models that account for the relevant microstructure features as well as the physics. Once these models are validated, we can exercise them towards designing new materials for these conditions.
I'm Faiza. I'm a PhD student in mechanical engineering here at University of Alberta. My work is on developing high-performance aluminum alloys for hydrogen storage applications using laser powder bed fusion. So we aim to develop materials that are lighter, stronger, and more resistant to hydrogen embrittlement, which is a major challenge in clean energy systems. An important part of my work is powder preparation. So this is where the ball mill comes in. And how it works is that by rotating jars that's filled with powder and balls, and as the machine rotates, the balls will move around, hit the powder, breaking it down and make it finer, and also due to the impact and friction, the powder will mix uniformly. Over the time, this mechanical process will allow us to have a finer powder and a more uniformly distributed powder. Our next step is to use this powder for laser powder bed fusion to prepare test samples and study the effect of the processing parameters on the microstructure and properties, especially in extreme environments like high temperature and hydrogen exposure. After this step and the powder is ready, I use this powder to fabricate test samples using laser powder bed fusion. So I would say like this whole process from preparing powder and also manufacturing using additive manufacturing techniques will help us to develop new materials that work for future energy systems.
We design the materials, we test the materials. To do this, we use advanced modeling techniques that allow us to capture different physics or different features across length scales, which then can inform the manufacturing, the 3D printing of these materials in Mostafa's group.
We work in various energy aspects. So we work on nuclear energy, hydrogen reactors, another application or another energy application that we rely on. We also work on defense application with Jamie and other collaborators. So we look at manufacturing methods that can be used for defense applications and aerospace.
My name is Assad. So I'm a postdoctoral fellow in the Alberta Next Generation Additive Manufacturing Lab, and I'm also an academic teaching staff in the mechanical engineering department, so I teach on the side as well. And my work basically focuses on developing laser additive manufacturing, nickel-based materials for small modular reactors for nuclear applications. There's a lot of tasks involved, starting from the materials development into the process development as well, building the components and characterizations as well.
3D printing of metals and ceramics, there are three big areas of application or areas of interest when it comes to 3D printing of metals and ceramic. One, complex designs. So designs that are very hard to produce using traditional manufacturing methods. You rely on additive manufacturing because it allows you to do that. It's a unique process or unique technology. Number two is advanced materials. Materials that were very hard in the old days or in the past for us to process them and manufacture them, but they can be used in additive manufacturing. And number three is room for improvement. It's always hard when it comes to manufacturing to improve the material and the design together. You will have to repeat a lot of things. So when it comes, for example, to machining or forming, if you change the material and it changes the design, then it become like have completely different conditions. That's not the case when it comes to additive manufacturing. You can always relate things and upscale it for you to make those changes. So there are a lot of room for improvements. And that brings us to aerospace, defense, and energy. So the overlap or the common thing between those three industries, they all have complex designs, they all have advanced materials, and they all look for room for improvement.
My name is Krutskaya Yepes. I am a graduate student at the University of Alberta. My research focuses on studying laser powder bed fusion of nuclear-grade materials to fabricate critical components for various types of small modular reactors. How laser powder bed fusion works? Here we use a high-power laser to fully melt and fuse metal powder, following a specific pattern that matches our design. We can choose the design like a simple shape or a complex shape. In this process, what we did is like to deposit a thin layer of metal powder over a metal build plate. Then our laser scanned the whole layer. After that, our build platform moved on, and a new thin layer of powder is spread again. We repeat this process until a complete 3D part is fabricated.
While printing is happening, we also do in situ monitoring to monitor the formation of every single layer of the 3D printed parts. So as you can see on the screen that we have, so we have different parts over here, cubes and dog bone shapes, which are useful for us for further characterization. And we have data on every single layer, and we can check the porosity, we can check the temperature distribution, and that will give us some non-destructive type of analysis and tests to check whether there is some pores inside, defects inside the components, and that will be useful for us for further analysis and characterization.
Combination of both techniques allows us to fabricate high-performance components and guarantee that these components will satisfy the necessity of the designer.
We work closely with our nuclear collaborators, and those components will be tested in their facility for corrosion testing and for high mechanical performance.
So for us, we look at the manufacturing conditions. So those are variables for us. So laser, we talked about lasers. My lab, we have two well-established laser manufacturing methods for 3D printing of metals and ceramics. So laser powder bed fusion and laser directed energy deposition. So we look into the laser process parameters. So just to simplify what those laser process parameters, think about the laser energy, how much power you can get in from the laser. And we do those as variables, and we change them, and we look how the material will perform during the manufacturing process. But that's one angle. There is another angle that we have to look at the post-processing. So before we send the material for testing, either to our collaborators or to Jamie Lab or to other labs, do we need to do some post-processing, and how those post-processing will also affect microstructure of the material and affect the performance of the material. So that's our input to ourselves. So based on the testing that we do in my lab, we use this input to fine-tune and enhance our manufacturing process as a next step. I guess I'll leave the second part for Jamie to talk about the type of testing when we send the samples to him and he tests them and he uses modeling to inform us.
The main conditions we would test under would be a range of temperatures, the rate at which we would apply these temperatures or mechanical loading, and then the environment that it's exposed to. So that could be a hydrogen-rich environment or a highly oxygen-rich environment. Running these tests under these extreme conditions are complicated, so we take great care with safety, and we take great care in planning the number of tests and the types of tests we run. The ultimate objective of running these tests is to validate the models. Once these models are validated, we can then exercise the models across a broader range of conditions, which then can inform on designing an optimal material composition or structure.
And this is a very good point that Jamie touched base on, is informing the model. So I guess I only mentioned about the inputs that we get from our collaborators and our partners here at U of A, that they test the material, but then we have to give them feedback. So our feedback is always to tell them how be honest first and tell them how the manufacturing process will perform. And they use those data to modify their modeling, for example. So Jamie will get some manufacturing data and can modify his models and validate them to be sure that those models are reliable to be used in other applications as well. So work closely with Jamie Group and other colleagues as well to get inputs from their material testing and their material design. So Jamie mentioned about modeling, for example. We get the results of those models that they develop. They tell us what we need to do. And once we get a homework, we go to the lab and we started to use the laser additive manufacturing to process this material to produce complex structures.
I'm Ziad Mohammed. I'm working on additive manufacturing for materials and high temperature applications, mainly focus on developing strategies to control cracks, optimizing the process parameters, also to produce high quality, dense ceramic builds to the ultimate goal, open a new pathways to produce complex, high-performance component that can withstand for nuclear environments. Laser-directed energy deposition, one of the top 3 deep printings for advanced materials, like high-temperature materials that can be used for nuclear environments. It's fully made in Canada.
I like that I get to have meaningful collaborations with my industry and government partners. I feel an obligation that we should be working on engineering problems that benefit Canadian society, and Mostafa and I work on these types of problems.
We wouldn't be where we are without that nature of collaborations. Input from material testing and modeling is a major factor for our success. So without these collaborations, we wouldn't be where we are. And our 2 groups work closely with each other. The CDM students that work with Jamie, like I consider them my students, and he does the same with my students.
My name is Monica. I'm a postdoctoral fellow at Amgen, and I work with additive manufacturing with ceramic materials. This is the dilatometer. Dilatometer is an equipment that used to measure the thermomechanical property of the material. That's important because when you're working with additive manufacturing, you need to evaluate some properties of the material. So using this make us able to analyze the properties. We need to ensure that the material will perform good in different environments, high temperatures, high corrosion systems. So we need to do some tests. And to ensure that the material will perform well, we use the dilatometer. To do it, we place the sample inside the furnace and then set a range of temperature. And the dilatometer will give us a thermomechanical property called coefficient of thermal expansion, CTE. And understanding the CTE will help us to understand how the material will perform under these extreme conditions, and then how to correlate the material properties of the sample that we are using for the applications in general, small nuclear reactors, for example.
In my lab, we focus a lot on multi-scale modeling. Materials exist at different length scales, so you can imagine there's a wind turbine that's 1 meter long. Within that wind turbine, there's a coating on it that may be at the millimeter length scale. Within that coating, there are grains, which may be at the hundreds of microns length scale. Within those grains, there are grain boundaries, and there are atoms, and so on and so forth. There's these different length scales that exist in the materials and within the structure. And what we want to do is we want to develop physically informed models that can account for how these materials behave under these extreme environments. Once we have these models, we can then exercise them to design new configurations of materials, new compositions of materials, or new structural geometries that have better performance and that last longer than conventional ones.
The dilatometer is connected to the software. When you set a range of temperature and measure the material, measure the difference in length of the material as the temperature changes. So this will give us like this difference in the length of the material, and then you're gonna have the CTE, which is this property that gives us the information about the thermal properties of the material.
What keeps me up at night is how the manufactured components will perform. And we have to take our job very serious because a component in a nuclear reactor cannot fail. This will be catastrophic failure. Same with hydrogen reactors, the same with defense applications. And that's what very big challenge. We take extra measures, safety measures during the manufacturing process. So we do in situ monitoring, for example, to monitor how the part is manufactured. If there are any defects, it alarms us that there are defects during the manufacturing process, but that's still not enough for us. So we have to send those parts to a lab like, very well equipped lab like Jamie Lab, and tell them, please do the worst conditions to those materials. Tell us how it performs. If you design your parts or those critical components at the worst condition, then they can be used in other easy applications. So that's what keeps me up at night, and this is a big challenge for us.
I'm Benson Ho. I'm one of the master students at the University of Alberta in Mechanical Engineering Department. I mainly research for high temperature corrosion So stuff like metal dusting for hydrogen embrittlement and including coking as well. And the main purpose of researching for coating for those is because in our reactor tube, we're doing methane pyrolysis, so which is breaking down methane into hydrogen and carbon. And when you have high carbon concentration, then your tube get corroded by carbon, and then eventually you'll create holes in your tube. So that's why we have to apply coating to prevent that from happening. So I normally will come heat up my sample first, and then afterwards, once they heat up to like 700 degrees Celsius or 900 degrees Celsius, then I'll start introducing gas. There's days where I'll be testing stuff like methane. I'll introduce methane in my system and then breaking it down into hydrogen carbon again, and then do the corrosion testing. So after that, I'll be characterizing my samples, evaluate the performance of my coatings. The main thing I'll look for is the microscopic pits that the corrosion environment eat into the material. Right? So I'll take my sample under the SEM, which is the scanning electron microscopes, and then I'll take an image and then see the depth of the pit. And then afterwards, I'll be weighting my sample, seeing how much of a material has been corroded, has been consumed away. And then aside from that, I'll also look at the phase changes. So using the XRD, which is the X-ray diffraction machine, right, to look at the phase changes of the material. Yeah, and that's basically how I characterize my sample.
There are a lot of overlap between the energy sectors. So oil and gas sector look for corrosion-resistant materials. Hydrogen look at for corrosion-resistant materials, but also materials that has high resistance to hydrogen embrittlement. You look at nuclear, they look at corrosion-resistant materials, but materials also that have high resistance to irradiation. So there are a lot of overlap between the energy sectors. And our job in manufacturing is to look at those overlaps so we don't have to repeat tests, for example. So if you test a material and you already know the corrosion resistance under certain conditions, if those conditions are similar in other applications, then we look at what is next. What is the next test that we need to do?
So this is the oven, right? And this can go up to 1200 degrees Celsius. And right now it's setting at 300 degrees Celsius, just the house oven temperature. So normally I'll have my sample in here. The white area is the one with coating, and the following area is the one that without coating. And then here you can see it get corroded pretty severely by oxidation. Right? This is nickel-based superalloy, but it also has iron in it, so that's why it's showing brown area of corrosion. So you can see with coating, you basically don't have any corrosion from happening. So this is just a few samples. These are our reactor tube. It get corroded quite severely. Here you can see like there's a lot of holes because of metal dusting. And that's just something that we have to be aware of when we are trying to produce hydrogen. So metal dusting, essentially, there's microscopic pits that has been corroded away. So if I put it longer, it'll potentially eat it all the way through the material and creating holes throughout the material. It can lead to gas leaks. It can lead to catastrophic failure, which is pipe burst, especially when you have pressure inside your reactor. This is very dangerous. So that's why we have to do testing and apply coatings to prevent that from happening.
While when it comes to 3D printing of metals and ceramic, I wish that more people knew that this is a standard manufacturing method that is used in some applications nowadays. I'm part also of the ASTM F42 committee for developing standards for additive manufacturing technologies. So I see that from the other side, we need those standards, and we need to tell people that this is what we can get from this process. So I hope people can know more about that. We don't do it alone. We work with collaborators that have expertise in those areas, and be sure that we use their expertise to enhance and modify our manufacturing process. Building collaborations is a long-term job. It's not just today. Maintaining it is more important than just building an initial collaboration. And that's what I've been working on, and that's what will be my goal for the coming 10 years, is to maintain those relationships with industry and with my collaborators here and my partners here at U of A and other universities across Canada, and help my team to grow.
The accumulation of my research in the last 10 years has led to a few things. One, the Center for Defense and Dual Use Technology, which is the only defense center at a university in Canada, and growing to be one of the largest centers within the Faculty of Engineering currently. As an outcome of the research, there's been a number of products that have been developed that keep Canadians safe, as well as grow export opportunities for my industry partners. I'm also most proud of the employment that the students have gotten after leaving my group, either in academic positions, leading industry research groups, or working for the Department of National Defense, keeping Canadians safe. You know, energy helps civilian applications. Energy is also very important for defense. We have bases in the north that need things like small modular reactors to support them. We also have initiatives within the federal government to go green with our defense platforms, and so hydrogen production, nuclear, renewable energies becomes very important in meeting Canada's objectives of making a greener defense system. Yeah.